This diagram profiles energy changes as the salt sodium chloride is formed. We need to start somewhere. We don't have to know the exact energies of our starting materials, but our starting materials are atoms of sodium in solid form. You know, sodium solids have low relative energies as solid, so there is motion in the particles, but they're just kind of sitting still, moving in place. Chlorine is a diatomic molecule with 2 atoms of chlorine moving rather fast as a gas, so I'll put some whizzy lines showing their motion. And so we have 4 atoms of solid sodium, I could have drawn any number, and 2 molecules I'm showing here of chlorine gas in their initial energy state. We don't know exactly how much energy each of these contain, but that's not as important as the changes that happen throughout the process. Since sodium is in the solid form, one of the first changes we have to do is make the sodium be found as a gaseous form. So we would have 2 plus energy in and give that enough energy to vaporize. And so now we have some very fast moving sodium particles as a gas form. That energy to go from solid to gas is known as the heat of sublimation. This is approximately 121 kilojoules of energy to make 1 mole of solid sodium turn into 1 mole of sodium gas. Now that the sodium is in gas form, sodium needs to be ionized. So we start with the gaseous sodium atom, and it becomes a sodium ion, which is much smaller, by losing an electron from its valence shell, and now we have the sodium plus 1 ion. That's known as ionization energy, the energy needed to remove an electron from a neutral atom. And this is a much larger energy. This is about 500 kilojoules per mole of sodium gas. The next energy will be breaking the bond between the 2 chlorines. The chlorine was already found as a molecule in gas form, but we need to break it into chlorine atoms. So we need to break the covalent bond between the 2 chlorine atoms and break it into the 2 separate chlorine atoms. This is known as the bond energy, and this one's about 100 kilojoules per mole needed to break that covalent bond. Now that we have chlorine atoms, chlorine needs to be ionized. Chlorine atoms as a nonmetal, tend to add electrons, and this is known as electron affinity. So my chlorine atom is going to gain an additional electron to become a little bit larger chlorine ion. So the chlorine -1 ion, by adding an electron, actually releases energy. This is an energy releasing process known as electron affinity, and this is approximately 355 kilojoules of energy per mole of chloride ions that we form. And if this is where we stop, because now I have chlorine ions and I have sodium ions, that should be where I stop. But if you look from where I started at the initial energy state, I've plussed in almost 700 kilojoules of energy, and I've only released about 350 kilojoules of energy. So I still would have an energy consuming process. But if I have 1 mole of sodium ions and 1 mole of chloride ions, they don't just partner up in a 1-to-1 ratio, but they arrange themselves in a 3-dimensional crystal lattice. The energy release as this lattice forms because of the electrostatic attraction between the cations and the anions releases a huge amount of energy in the neighborhood of about 790 kilojoules per mole of chloride and sodium ions that arrange to form the sodium chloride crystalline salt. So actually, I am ending up with a net release of energy. If I take sum of all my energy increasing steps, sublimation, ionization energy, and bond energy, and compare it to my energy releasing steps of electron affinity and lattice energy, I find that the heat of formation for sodium chloride is about 400 kilojoules per mole of sodium chloride formed. That's the difference from where we started and where we wound up. And that's this orange line here, and that's known as my bond energy or heat of formation.